Well, let's say that you have 2 moles of an ideal gas and you got a pressure of 3 atms and you had a temperature of 300 degrees Kelvin, and you want to calculate what volume does your ideal gas occupy. And this is when you use the ideal gas law. All right, so to solve the problem, you're going to use something called the ideal gas law. And the ideal gas law is this formula I have boxed: PV equals nRT, where this is our pressure. In this case, in this video, we're going to use ATMs for our pressure, volume, and the volume in this case, we're going to use liters. Moles of gas, N represents the moles of gas that we have. So in this case, we have 2 moles, right, in the problem. R is going to be our ideal gas constant. And usually when you're doing these problems, your teacher is going to give you the ideal gas constant, or, they might have like some sort of textbook, some sort of reference guide. One ideal gas constant is just 0.0821 liters ATMs over moles times Kelvin, and they can be in different units. You can have multiple like ideal gas constants depending on what units you're using. But in this video, we're just going to use this ideal gas constant, and we also have in our formula temperature, and in this case, our temperature should be in Kelvin. So let's plug in what we know into this formula. We know that our pressure is 3 atms. 3 atms. We know that our volume, well, we don't know our volume actually, so let's just call that X. We know our moles of gas, right? The moles of gas, that's our N part. That's going to be 2.0 moles. I'm just going to write 2 moles. Times our ideal gas constant, which is R. Well, we know what that is. 0.02821 liters ATM over moles Kelvin. And we know our temperature in Kelvin, 300 degrees Kelvin. So now it's just a matter of solving for X. And how do we solve for X? Well, what we're going to do is just divide both sides by 3 atms to isolate our variable, right? And 3 atms. And you'll see how our units cancel out, right? This right over here is going to cancel out, right? Because we just isolated X. And you'll see how our moles cancel out. Our ATMs cancel out, right? Our temperature, the Kelvin unit, cancels out, and we're left with liters. And since we're talking about volume, right, we're trying to calculate volume, and if all our units cancel out when we solve our problems and we end up with liters, well, we're heading in the right direction, right? So now this is just a matter of calculator. So 2 times 0.0821 times 300, and then that's going to equal 49.26. I'll divide all that by 3, and for your final answer, you should get that X equals to 16.42 liters, and rounding to the correct number of digits, I should have put a decimal here. Just pretend I put a decimal here at the end of the problem. But if we're rounding to 2 digits, let's say we round to 2 digits, so our volume, the volume that the gas occupies, it's going to be 16 liters if we round to 2 digits. And that's going to be our answer. A gas occupies a volume of 5.0 liters at a temperature of, so let's put a decimal over here, so 27 with a decimal at the end, degrees Celsius, and a pressure of 1.2 atms. How many moles of gas are present? So once again, let's write out our formula. PV equals nRT. right? We know our pressure, right? We know our pressure. That's going to be 1.2 ATMs. 1.2 ATMs. We know our volume. That's going to be 5.0 liters. 5.0 liters. We know that's going to be equal to the amount of moles of gas. Well, we're trying to solve for that, right? So let's call that X times the ideal gas constant. The ideal gas constant, that's going to be 0. You can check back before, like a couple of seconds ago, to see what the ideal gas constant is. 0.0821. And then that's going to be liters times ATM over, it's going to be over Kelvin times moles. Kelvin times moles. And then that's going to be multiplied by our temperature. Now the temperature right over here is 27 degrees Celsius. But remember back to what I said before, right? When you're doing the ideal gas laws problems, right, the temperature should be in Kelvin, right? So that when you're actually plugging it into the problem, right? Imagine if we plug 27 degrees Celsius, right, into this equation, right? You can see how the Celsius and this Kelvin unit doesn't match up. Therefore, you can't cancel out the units and you're not going to get the correct answer. So just make sure that whenever you're doing these types of problems, make sure that your temperature is in Kelvin instead of degrees Celsius. So how do you convert degrees Celsius to Kelvin? Well, you just take your degrees Celsius and just add 273 to it. So 27. So this is going to be, just plug this into my calculator. So 27 plus 273, that's going to be 300 degrees Kelvin. So now you see how the Kelvin here matches up with the Kelvin in the ideal gas constant, right? And kind of the way I like to think about it is just make sure that all your units, right, match up with the units in your ideal gas constant. And if, right, you have ATMs right over here, you have liters, which is right over here, you have Kelvin right over here, and you're trying to solve for moles. So let's solve for X, right? Let's solve for X. So what we're going to do is we are going to divide both sides by 0.0821 liter ATM. I'm just going to make a cut here so that you don't have to see me writing this whole thing. So now what we're going to do is we're to isolate X, right? We're going to divide both sides by this whole thing right over here. So yeah, we divided this side by this, and we divided this side right over here, the left side, by this. And you'll see how, right, all of this is just going to cancel out. So we have X isolated, which is amazing. Oh, I accidentally erased the... Okay, so I'm just going to erase this real quick. So all of that stuff cancels out. And you'll see how when you're dividing all of this thing, your Kelvins cancel out. Your ATMs, right? It's on the top and bottom. That's going to cancel out. Your liters are going to cancel out. And because you're trying to find the amount of moles, right? How many moles of gas are present, and you're left with moles as your unit, well, we're all good. And now it's just a matter of plugging this into your calculator. So 1.2 times 5 which is 6, divided by 0.0821 times 300 and times 300. And when you plug all this into your calculator, right, I'm just going to round to 2 digits. I'm going to round to 2 digits because we have 2 sig digs on all of our given information. So this is going to be x equals 0.24 moles of gas. Yeah, so if you plug all this junk into the calculator, you're going to get x equals 0.24 moles of your gas. And that's going to be your answer, rounded to 2 digits. Okay. You have a sample of oxygen gas with a mass of 16.00 grams. The gas is at a temperature of 30, let me just put a decimal here, 30 degrees Celsius, and a pressure of 3.0 atms. Given that the molar mass of O2 is 32 grams per mole, calculate the volume of the gas. So once again, I'm going to write out our equation. PV equals nRT. Now, what's the first problem you see in? What's the first problem we kind of have right now? Well, one of the problems we have is that our temperature is in degrees Celsius, and right, just like the problem before, our temperature needs to be in Kelvin. So 30 plus 273, and we converted it into kelvins, right? This is just going to be 303. So that's kind of our first problem taken care of. Well, what's 303 degrees Kelvin. So that's kind of our first problem taken care of. But what's kind of our second problem? Well, we have pressure, right? We know that the pressure is 3 atms. We're trying to calculate the volume. Let's call that x. We know the amount of... Wait, what? We don't know the amount of moles of gas, right? It says it has a mass of 16 grams, but they don't give us the amount of moles of gas. Oh, how would we do this? Well, we know that we have 16 grams of oxygen gas. And we know that in 1 mole of oxygen gas, right, it weighs 32 grams, right? So the molar mass of oxygen is 32 grams per mole. And all this means is that if we were to take 1 mole of oxygen gas, we would expect it to weigh 32 grams. So if we have 16 grams of oxygen gas, well, we just multiply it by this conversion factor, and we're going to get 0.5 moles of oxygen gas. And this kind of makes sense, right? If we have 32 grams for 1 mole, well, if we have half the amount of oxygen gas, half the amount of weight, well, we're going to have half the amount of moles, right? You see how as the grams decreased by a factor of 2, the amount of moles we have decreased by a factor of 2. So now we have our moles of oxygen gas, so 0.5 moles of oxygen gas. I'll just write 0.5 moles. We know the ideal gas constant. Scroll back to the video if you forgot that. So 0.8. Pretty sure it's 821, and then this is gonna be. Wait, what was the unit again? Oh yeah, liters times ATM. Liters times ATM over moles times Kelvin. And then this is going to be multiplied by our temperature in Kelvin. This thing right over here. It's Kelvin. How do we solve for x? Once again, just divide both sides to isolate x. Let's divide both sides by 3 atms. 3 atms. So now you see that all of this cancels out. And let's see if our units cancel out to make sure that we have the correct answer. Well, we can see our moles right over here. This is at the top, this is at the bottom, so they cancel out. Our temperature Kelvin, and Kelvin cancels out. Our ATMs, right, they cancel out. And, well, we're left with liters. And because we're trying to find the volume of the gas, because we're left with liters as our unit, well, we're all good. So if we plug this into the calculator, 0.5 times 0.0821 times 303, and we divide this by 3 ATM. That can't already cancel out, so we just divide it by 3. And we are going to get x equals, how many digits are we rounding to? Okay, so we're going to round this to 2 digits, okay? We're going to round this to 2 digits. So x is going to be equal to 4.1 liters. 4.1 liters. Meaning that the volume occupied by the gas, right? The volume of the gas, that's just going to be equal to 4.1 liters. It was 4.14 liters, but I rounded to 2 digits. I rounded to 2 digits because of the 30 degrees Celsius.